Harmonic oscillator quantum computer. We first discussed the simple harmonic oscillator. Let us consider the particle in a parabolic potential well. The potential energy operator is Vx equal to half m omega square x square. In a classical world, an example of such a potential would be a mass on a spring which oscillates as energy is transferred between the potential energy of the spring and kinetic energy of the mass. Another example is a resonant electrical circuit with the energy going back and forth between the inductor and capacitor. In both these systems, the total energy is a continuous parameter. In the quantum domain, the total energy of the system can only take a discrete set of values. A set of discrete energy eigenstates of a simple harmonic oscillator can be labeled as ket n, where n goes from 1, 2 up to infinity. The relationship to quantum computation comes by taking a finite subset of these states to represent qubits. These qubits will have lifetimes determined by physical parameters. Unitary transformations can be applied by simply allowing the system to evolve in time. We now use the simple harmonic oscillator states to implement the C0 gate. The C0 operation is represented by the following set of equations. We know that whenever we have the control qubit as 0, the target qubit remains unchanged. Whenever the control qubit is 1, the target qubit is flipped. Now, if you start off with ket 0, 0, it remains 0, 0, ket. If you start off with a ket 0, 1, it remains a ket 0, 1. If you start off with a ket 1, 0, the target qubit 0 is flipped to 1 and the resultant ket is now ket 1, 1. If you start off with a ket 1, 1, the target qubit 1 is flipped to 0, so ket 1, 1 becomes ket 1, 0. In this case, we have used the subscript L to clearly distinguish logical states in contrast to the harmonic oscillator basis states. The right hand side shows the schematic of the C0 gate. Now we need to encode these qubits using the mapping as follows. We take ket 0, 0 to go on to ket 0 of the ket 0 eigenstate. Ket 0, 1 goes to ket 2 eigenstate. Ket 1, 0 goes to ket 4 plus ket 1 divided by root 2 eigenstate. Ket 1, 1 goes to ket 4 minus ket 1 upon root 2 eigenstate. Now let us suppose at time t equal to 0, the system is started and it starts in a state spanned by these basis states. We simply need to evolve the system to a time given by pi upon h cross omega. This causes the energy eigenstates to undergo a transformation represented by ket n going to exponential to the minus I pi a dagger, which is equal to minus 1 to the power n ket n, such that ket 0, ket 2 and ket 4 will remain unchanged, but it is only the sign of ket 1 that will be flipped to minus ket 1. This is how we get the required C0 gate transformation. There are certain drawbacks associated with implementing a simple harmonic oscillator as a quantum computer. The eigenvalue spectrum of any unitary operator is not always known. Knowledge of the eigenvalue of the spectrum is equal to knowing the solution. The technique used above does not allow cascading of one quantum computation with another. And most importantly, the idea of using a single simple harmonic oscillator to perform quantum computation neglects the principle of digital representation. Now, this is explained in greater detail in the next slide. Let us understand why using a simple harmonic oscillator as a quantum computer is actually a flawed idea. A Hilbert space of a dimension 2 to the power n is mapped into a state space of a single harmonic oscillator, and it would have to allow for the possibility of states with energy 2 to the power n h cross omega. Now, the same Hilbert space can be obtained by using n two-level quantum systems which has an energy of most n h cross omega. Similar comparisons can be made between a classical dial with 2 to the power n settings and a register of n classical bits. We have to remember that quantum computation builds upon digital computation and not analog computation. Here we summarize how theoretically we propose to use the harmonic oscillator as a quantum computer. We've already seen that it's actually not possible. We have qubit representations given by energy levels ket 0, ket 1, right up to ket 2 to the power n of a single quantum oscillator, and these give us n qubits. Then we need unitary evolution, that is arbitrary transforms U are realized by matching their eigenvalue spectrums to that given by the Hamiltonian H equal to A dagger A. The initial state preparation has not been considered. The readout has not been considered. And the drawbacks are that this is not a digital representation. Also, matching eigenvalues to realize transformations is not feasible for an arbitrary unitary transformation which generally have unknown eigenvalues. Now, before I conclude, I'd like to point out that this description is utilizing the fact that it is assumed that you know the derivations, you know how a harmonic oscillator operates as a quantum system. But for those of you who do not know this, what I will do is I will create a associated PowerPoint presentation in which the quantum harmonic oscillator and the anharmonic oscillator is discussed in detail. So we will start with the Schrodinger equation, we will do the basics of the quantum mechanics, and we will also see the significance of A and A dagger. That in itself is a pretty interesting topic, and it will just be a subsidiary, or what shall I say, accompanied presentation to what I have just taught. For those of you who already know it, great. And for those of you who don't, there is a subsidiary PPT coming up, and also we will be doing one more presentation on optical photon quantum computer. So hopefully I shall be able to put forth 2 presentations tomorrow morning. Thank you so much for your time, and I hope I have been able to explain, number 1, theoretically how to use a harmonic oscillator as a quantum computer, and number 2, why it is not practically feasible.